this paper, about this blog post, and get a sense of what your takeaways were from it, and share some of my takeaways, things that I thought were interesting from the paper and from the blog post. Hopefully, it was interesting to read. I know I find it's a really interesting post just because it's coming from someone who's worked on compilers for a long time, and it's interesting sort of at the programmer level. To think about like what you can do to help the compiler and what you need to be concerned about in terms of writing code and running that code when you might have undefined behavior. So the first thing I wanted to point out was that I really like the statement they have early on in the paper. This is right before the heading "Advantages of Undefined Behavior in C" with examples. But they talk about sort of the fact that there's no magic bullet to optimization for C programs, and that at a high level, they say at a high level, compilers produce high performance apps by A, doing a good job at bread and butter algorithms like register allocations, scheduling, etc., knowing lots of tricks, peephole optimizations, loop transformations, etc., applying them whenever profitable, being good at eliminating unnecessary abstractions, like inlining functions, eliminating temporary objects, and not screwing anything up. And that while some of these optimizations may sound trivial, saving one cycle out of a critical loop can make some codec run 10% faster or take 10% less power. So I think it's just a nice summary of sort of the optimization section of this course, right? This is what the compiler does to optimize code. Knowing a lot of these individual, seemingly simple algorithms and applying them together, sort of all together, whenever it's profitable to do so. So when there's more profit than there is risk, and eliminating these unnecessary abstractions from languages. So trying to make things cheaper, even if they are easy to program at a high level in the language. And then obviously the last point being not screwing anything up. So that's the correctness part of optimization, that we sort of have this profit risk and correctness. Not screwing anything up is sort of the most important point, that we want to make sure that with respect to the language specification, the optimizations that we perform are in fact correct. So that's what this whole post is about, right? Is being correct with respect to what the language has specified, rather than necessarily being 100% correct. Do any functional languages have undefined behavior in their spec? Not that I know of, but I could be wrong here. It tends to be that these are lumped in with the comment above this in the paper, is that languages like Java and many other safe languages have gotten rid of undefined behavior because they want safe and reproducible behavior across implementations and are willing to sacrifice performance to get it. That said, there are things that tend to be common to most languages, like unsigned integer overflow. That I would maybe expect, like assigned integer overflow and shifts, I would maybe expect to be a source of possible undefined behavior in these types of languages. Mostly with respect, though, to in those cases, probably to like the integer output that you would get from some mathematical operation, because other languages tend to not let you mix things like memory accesses with integers. So a lot of the undefined behavior that comes into play in C with unsigned integer overflow and shifting ends up being because of the fact that you end up indexing into an array or doing some pointer arithmetic that relies on that undefined behavior. And then that can cause very odd things to happen when all of a sudden you're accessing memory all over the place. But yeah, good question. Not that I know of, but that would be interesting to find out for sure. Okay. So any other thoughts leading into the sort of, examples of undefined behavior?
Sir, I had a quick question. Something that was on the quiz. So with initialized variables that are defined, I thought that the reading kind of said that like you never know what would happen with them.
Mm-hmm.
On the quiz, I think the answer was like false or something. Could you just like explain that?
So an unanalyzed, so the question was on the quiz, an initialized variable will always cause the program to behave in an unexpected way. So this is the first one, right? So use of an uninitialized variable is something that the compiler doesn't handle for you because it would be expensive to do so. So I guess the question is then, when can an uninitialized variable not cause the program to behave in an unexpected way?
So like the quiz said that like if it just happens to initialize to what you want it to be, like 0 or something.
Right. So, if we have, if you have two functions, maybe I should actually present to show this. So let me do that real quick. So, we have two functions here. I'm going to call foo, and then I'm going to call bar. Let's get that. I'm going to pump this up a little bit. Make it a little easier to see. So let's say we have two functions here. We have foo and bar, and I'm going to write these foo, and I'm going to write bar. So I'm going to have int x here, and I'm going to have int x equals 0 here. What is this program likely to print out if I print y here?
Probably 5.
Probably 5. Yeah, so let's see if it actually does it. It may not, due to the fact that this is an online thing. So it doesn't here, but theoretically speaking, right, we call foo. Foo initializes some position on the stack to 0, right? We call bar. Bar doesn't initialize that position, but due to the way that we build the stack from top to bottom, or like bottom to top, x should end up in the same position in bar as it was in the function foo. So theoretically, that x does get initialized to the value that we expected. Maybe we expected to initialize it to 0, but we didn't. But the fact that we initialized it in another function, or we initialized that memory in another function to be 0, it's possible that whenever we run this on some system, that this ends up copying that 0 basically over to here, or that the memory location just happened to be 0 when we came into that function. So this is sort of the point of that, is that, we don't necessarily have, we don't always have the case that this will cause the unexpected behavior. It is still undefined, but it's undefined in the sense that like the program will work if the memory happened to already be the value that we wanted it to be. Okay. And there are a lot of other cases that this can happen, right? Like if we have things that are on the heap, if they happen to come from a page that was zeroed out. So often, a trick to sort of zero out memory quickly is to have a read-only copy on write page. That Linux has this page of memory that is always there, called the 0 page. So it can be shared between multiple pages in the system. If we're just reading zeros, basically, it's okay to keep reading zeros. So if we haven't initialized memory yet, if we haven't done anything to it, we can have this single page of memory that is just zeros that we read from until we actually do something to it. And then when we actually write something to that page, we copy that page out. So that's a quick trick to like sort of zero read-only memory. Is then we can point that page that we want to zero out back to this 0 page. So that means that like if our memory that we allocated with malloc is coming from that 0 page, it might actually end up being zeroed out memory that we get from the system, but that's not guaranteed to be a thing by the C programming language, mostly because then it would have to be required that like every operating system that's going to run C programs has to implement that the same way as Linux does. So it's very possible basically that we have a case where this uninitialized variable does allow the program to behave in the expected manner, but most of the time it won't. It's undefined by the language specification. So I hope that helps. Okay, so that's uninitialized variables that I think are an interesting sort of detail here. The other thing they talk about are sort of integer operations. So signed integer overflow and oversized shift amounts. So do we have any questions on those? Okay. Yeah, so I think those are fairly self-explanatory. The one that I did want to make here is there's been a push a little bit in sort of the research arena for, especially in C and C++, having sort of a verified C or C++. So this is sort of where what you might do is, you would have sort of proofs that your program works properly included with your program. And the compiler in this sort of case can kind of generate some of that proof for you. And so I used this for one of the courses I had during grad school. And it was interesting, but a lot of the problems you run into with that are dealing with signed integer overflow and oversized shift amounts. So many of the programs we write, we just kind of take for granted and assume that we're not integer overflowing. But when you try to actually verify and prove that your program works the way that it's expected to work, that integer overflow really starts to come into play. That ends up being a lot of the problems that you run into. And I think probably the case that like a lot of the programs that we write have possible integer overflow, but we've assumed as the programmer that it's just not going to happen. And so I think there's sort of an interesting thing there that we don't necessarily think about this very much, but it's definitely something that the compiler is taking advantage of. And it's definitely something that is a possible problem with a lot of the programs that we end up writing. Because we just assume like, yeah, the input from the user is not going to be over 4 billion, right? Or it's not going to be close to that 4 billion number that causes integer overflow, or 2 billion if we have signed integers. And so I think this is something we don't consider a whole lot. Maybe we should consider a little more, but it actually comes into play a lot when we do this program verification, to some extent, just because of the fact that to be correct, we have to make sure that we're not having this type of integer overflow. I think the other interesting point here is sort of on the oversized shift amounts. So this is where hardware really comes into play. And this sort of undefined behavior that can be caused by the fact that hardware can be designed in any way that the hardware designer wants to design it. And often that hardware is designed to be efficient, especially with regard to performance. So, so like these oversized shift amounts, it is platform dependent how that gets handled, and that's going to be handled in a way that the hardware, whatever way it's designed, this is the ALU. In that hardware, however the most efficient way is to design that ALU, that's what the hardware designer is going to use. And that may not always be the same exact efficient way to design an ALU on every single processor because of other platform specific issues. So they may decide to do different things whenever we have a shift that is too large. And because of that, we have this sort of undefined behavior caused by the hardware. Okay, so then next up we have sort of the type safety issues in C. So all of these can kind of be lumped together to some extent. The dereferences of wild pointers and out of bounds arrays, dereferencing a null pointer, and violating type rules. So these are all cases where we can end up accessing memory in sort of a different way than the computer might expect. And some of these are very reasonable things to do in practice. So I did want to give another example here. I'm going to steal presentation again if I can. Oh, there it is. It's hiding behind my glass of water. So I'm going to switch this to C++ for a second here, and not actually going to do much with the code here, but say we have a 3D vector class. We have some public methods on it, and our 3D vector is just int x, int y, and z. So we have a 3-element vector that we are going to be able to do some operations on. So we might have this case here that we have 3 variables, int x, int y, and z. We may want to, and actually I'm just going to make these public for simplicity. So we may want to make these, we may want to be able to basically like have a vector, and I might want to refer to x, you know, and assign values to x, y, and z. Sorry, and v dot y and v dot z. Right, so I can access these via the names of the positions within that vector. You know, so this is sort of a convenience thing for people who are, you know, writing mathematical code where they want to manipulate these based on the x, y, and z coordinates for a vector. And we may also want to have a method that says like, you know, operator this that takes a position within that vector and returns, you know, based on the start of the vector, we might want to return the position so that basically we can then say, you know, vector at 1 is equal to 5, and that would change v dot y. Used to hitting Control S all the time. So what we can do here is we can actually say, you know, int star v equals ampersand x, and then return v at position. And this is legal code. I believe this should work. It may have some bugs in it because I don't exactly remember the exact syntax for operator. I think this has to be an ampersand, maybe. Yeah. So we're just overloading the index operator on this class to allow us to index into this vector, basically allow us to treat it as an array. And what we're doing here is we're taking the address of x, using it as an array then, and returning that position within that array based on x. So this is legal code. It does a lot of these things that the post here is talking about. It violates type rules a little bit because we are, you know, casting, or we're not actually violating type rules that much, but we are taking a pointer to something and then treating it as an array when it's not actually an array, which is a little bit weird. So even though we're not violating type rules, we are sort of, you know, skirting the boundaries of what we should be doing with the code maybe. So what do we need to make this code like safe or well-defined?
Would you want to have those like 3 positions x, y, z just be like one array of 3 values? Because like you might not know that x, y, z are going to be right next to each other in memory.
That is true. We might have padding, so that could cause some issues here. I think given the way that this is set up, I believe that it will pack it together. But that is a good point, that this may be somewhat undefined based on whether or not there ends up being padding between x, y, and z. So it is possible for the compiler to sort of mess up our implementation here. But otherwise, you know, we sort of, for the semantics of this, we do want to be able to access this so that, you know, maybe I don't have this here, but, you know, I can say if I want to add, I want a method to like add all of the, or add one to each element of the vector, I can do this, right? I can say v at c equals v at c plus 1, right? So like this allows me a little flexibility in that I can, iterate over the elements of the vector and do something to them, or I can access them by name. So for convenience, like this is something that gets used in code, in like real C++ code, just for the fact that it gives convenience to the programmer to either work with the name members or with the sort of operator method. So what do we need to make this safe? Do this operator here. What could I add? Balance check. Yeah, so we could add, we have an assert. We could say, basically, assert that position is greater than or equal to 0 and position is less than 3, right? So if I assert this, my program's going to crash if I don't have this. I think this is also where you can have this string here that will print out then, or at least show when the assert fails. It's kind of a nice little hack to know, since a string is going to evaluate to not, or it's going to evaluate to a non-zero thing. You can always include sort of a message on this assert so that when the assert fails and they go to that line of code, the person reading your code can see what this assert was meant to check here. It's just a little hack to know. So this is checking just to make sure that we are within the bounds, but we don't necessarily want the compiler to do this for us, right? Because that would mean an additional, instruction here to check that position, an instruction here to check position against 3. Usually we don't have this sort of double-ended comparison operation, so we can't sort of make sure that it's in between those two things. We have to check the lower bound and we have to check the upper bound. There's probably some branching, possibly additional basic blocks, more control flow for the compiler to deal with. So there's a lot of stuff that happens to have this assert. So most of the time, C programmers, C++ programmers are going to choose not to have these, especially during like in production where, you're deploying this application, you want to have the best performance possible. So this sort of thing, doesn't always get included by the programmer, even, and definitely doesn't get included by the compiler. And that can mean that we can have very strange behavior. So I wanted to go back to the question 2 on the homework. So in the presence of undefined behavior in the code here, let's sort of assume here that we have this position, and then we end up doing something else with it, which is this switch statement that we had in class here. So change this to beyond x. Okay, so where do we make this on position? Okay, so what can go wrong with this code here? We have this setup where we have our switch. We have a switch based on this position. We're making the assumption that position is less than 2, and then we're switching on it. Usually, these switches end up getting implemented as a jump into a cable. So usually what happens here is based on position, we're going to calculate target equals current PC plus, position times, some sort of spacing. So, position times, maybe like OX1 or something like that. So if we assume that the code, each case statement is basically each case statement is 16 bytes away, we end up multiplying the position by 16 bytes, and we adjust the PC by that much. So that's how we jump from the switch statement to the actual case that we're going to execute first. So what can go wrong here? Especially, again, in the presence of threads, what can happen?
You have index out of bounds.
We can index out of bounds. What else due to the fact that it's actually jumping based on this position?
Like a race condition?
Yeah, so a race condition. So yeah, so what happens if we have, we basically check this position. So the compiler here is assuming that that position is less than 2. If position ends up being 10, all of a sudden, because some other thread comes in and changes it, now in this case, this is local, so this doesn't quite work, but we have code, let's say, that does have a global variable position or something like that. Now it does this computation to decide what code to jump to. And case 0 is at, PC plus OX10. Case 1 is at PC plus OX20. The calculation it's going to make for position 10 is going to be that we go to target equals PC plus, 10 times OX10. And now we're going to end up going to, OX PC plus OX AO instead. And that is, somewhere, who knows, in code. So this is a sort of corner case, but something that is important that sort of combines multiple types of undefined behavior. We have a data race. So, some other code changes our value here. We have an optimization based on the fact that locally the compiler looks at this, within the function, so global optimization, the compiler looks at this and says, okay, well, if position is less than 2 is guaranteed here, and the cases are 0 and 1, I know that I can do this optimization where I transform this into a jump based on the current PC and, sort of line up the code so that I can just jump based on the value of position. But then because of the fact that there's a data race, that ends up leading us to execute some undefined code. And, in a more malicious case, this could allow the attacker to basically change position to be whatever they want to, and redirect to any code that they want to redirect to. So this is sort of this sort of bad security case here. This is an example from, there's a primer on memory consistency and memory coherence that uses this example that is sort of the worst case scenario of data races mixed with undefined behavior. Okay, so any other questions on sort of the first part of the blog post here, these types of undefined behavior?
I'm not totally clear on what it means by dereferences of wild pointers.
Okay.
I'm not sure what wild pointers means.
Let's see. Where exactly is that? Oh, at the top here. Dereferences of wild pointers. I think that just sort of means anything that is not currently valid memory. This is out of bounds array accesses. It's also, accesses to memory that has been deleted. So, we have int star x equals, new int. We delete x, and then we define float star y equals new float. And then we do x equals 5. Right? So x is no longer valid memory because we deleted it here. Float y is likely in the same position as x was because float y is 32 bits and int is 32 bits. So whenever the allocator sees that we want new memory and it has a free block of 32 bits, it's fairly likely to reallocate that block. And so when we modify the value of x here, we're actually writing that into probably the space that's now occupied by float y. And if we print out this float y, we're likely to get a very strange value because we're taking something that is being printed as like IEEE floating point format that is coming from an integer. So I think that's all they really mean, is that we're dereferencing any pointer that is not the actual valid pointer that it should be there. Which does include null, includes things to freed memory, and anything that's out of array bounds. So this could also be like if we did here, while we still have valid memory for x, we did x equals x plus 1 and then dereferenced x. And so x is obviously out of bounds at that point because it has gone past the bounds of the single integer that we allocated.
Okay, thanks.
Yeah, no problem. Any other questions on this part of the blog post? Okay, so let's move on to part 2 here. I'll try to speed up a little bit because I don't want to take too much time on the rest of this. So, so this part, they sort of talk about, how these compiler optimizations can interact. And I like the sort of running example they have here is interesting. So I'll just put this up on the screen that they have defined for us. So they have this void contains null check int star p. And here we have int dead equals star p. And if p equals 0, return null, or sorry, return. And then star p equals 4. So we have a case here that basically they check for the null pointer in this part of the code. So if we have a null pointer, we don't end up writing to p here, right? So the problem is that right here, we see that this is dead code, right? Dead is not used anywhere in this function. We know that because of the fact that this is a local variable, we can do a global optimization on the function, or maybe even a local optimization to eliminate dead code and see that this is no longer needed. So this is dead code. It can be eliminated. So we can comment that out. So that's no longer there. And this occurs due to dead code elimination. Then we might have a redundant null check elimination. So because of the fact that this is eliminated, this is no longer a redundant null check because of the fact that this is happening before an access to this pointer. So in the case that the compiler runs dead code elimination and then redundant null elimination, it's okay because we do end up keeping this null pointer. However, in the case that it runs redundant null elimination and then dead code elimination, this might be a little bit different. So here, let's say this is not dead code yet. We're running redundant null elimination first. So we've done this access to int dead equals star p. Then we check if p equals 0 return. What's going to happen here if p is null? So when we run this program, if p is null there, what happens?
We don't know. Could be anything.
Could be anything. What happens on our Linux systems if we run this?
Dereferencing a null pointer.
Yeah. So it should segfault, right?
Right.
So if we dereference a null pointer, our program is going to segfault, or we get the sort of undefined behavior of whatever the system does when we dereference a null pointer. So that means that it's redundant to check if p is null after we've already sort of failed, right? So on my Linux system, if I do this, int dead equals star p, and p is null, this code is going to just segfault, crash anyways. So it's redundant for me to check after the segfault if we segfaulted, right? That's going to kill the program anyways. So the redundant null check elimination can get rid of all of this code. So if we run redundant null elimination first, we see that this is a redundant null check, and we get rid of it. Then we run dead code elimination, and we get rid of this because we aren't actually using dead. And these are independent passes, so it doesn't really think about the fact that that we just eliminated a null check, and now this code was our null check. So because of the fact that we don't sort of pass that information from the redundant null elimination to the dead code elimination pass, we can then eliminate this as dead code, and we end up with this situation where all we have is p equals 4. And so now the programmer thought that they had a null check in this code, but when it comes down to it, the compiler has actually eliminated that null check. And now when we write to p equals 4, this is just a possibly write to null that might crash our program, and otherwise does not have the check that we thought we had to prevent that write to null and crashing the program. So this means that we have sort of undefined behavior again that may or may not impact the program. So this might crash our program, this might not crash our program, and it is totally dependent on the order in which we optimize the code. So this is where if you run your code with -0, you might get different behavior than if you run your code with -02, because there may be optimizations that apply that end up changing the behavior of the code based on the ordering of optimizations. So the sort of critical thing here is that the order does matter, and that we can't necessarily rely on the fact that if our code runs without optimizations, that it will run properly with optimizations, and vice versa. There are cases where an optimization might make your code run correctly, and then when you get rid of that optimization, it breaks all of a sudden. Okay. And things like this can cause major issues with security. So we have many cases where because of the fact that it eliminates a null check or eliminates a balance check or something like that, this ends up causing security issues where all of a sudden our optimized code might have a security flaw that we didn't have in the regular code. Okay. Other interesting things from this section. So I think that it was interesting that they sort of give the note that you should try to use O0 if you are debugging your code, because then you don't get the optimized version. I do think it's important though also to, especially if you're working with like parallel code, to, you know, debug at multiple optimization levels. So if you're working with things that might have data races, you want to debug at 0, you want to debug at 01, you want to debug at 02, you want to debug at 03, because that's more likely to sort of hit the possible code interleavings that might occur when you're running in parallel. So it's usually pretty important to try to debug at all optimization levels just to make sure that you've hit everything that might possibly happen with this type of behavior. This sort of goes into the details about question 3 that Rupan brought up, that, you know, we could have working code that uses undefined behavior might work sometimes. You know, an uninitialized variable might get 0 initialized by luck, and then might share a different register or share a different space on the stack and no longer be 0 initialized by luck. A number of these other optimizations, like, you know, inlining, loop unrolling, memory promotion, may get better and then change the things that you know, that were working in previous versions. And then finally, their big point at the end is that there's no guaranteed way to find all of these things. You know, we can use things like static analysis to find issues that might be in our code. We've talked about that before, that, you know, with static analysis, you might say, you might run into too many errors and end up not looking at them. We can run dynamic tools. Dynamic tools are helpful because they only find real errors, but they have to actually encounter that error in the run of code that you ran to find that error. So, you know, if the compiler optimized things this way when you ran valgrind or some other memory bug detection tool, this wouldn't be a problem because it would see that there's this null check and then the access, and it would, you know, not have the issue that we were running into. If you then optimized the code and didn't run valgrind on that code and ran it this way, that it did redundant null check and then dead code, all of a sudden you run into this problem where you don't have that null check anymore. So dynamic analysis is only going to find things that you actually see during a run of the program. So there's sort of, you know, downsides to both of these, and it's very difficult to basically, you know, figure out if there's undefined behavior within a project or not, because this is a compiler specific thing. So we really can't look at like the source code and tell all the time if there's going to be undefined behavior. You know, a lot of the common cases we can detect and we can prevent those. And, you know, as a programmer, you should be looking out for those and trying to eliminate them when possible. But it's not always feasible. Okay, so why can't we warn when optimizing based on undefined behavior?
Can you say that again? Why can't we what?
So why can't we warn a programmer that we're optimizing based on undefined behavior? It's hard to know every possible case, yeah. That's definitely one thing. What else?
Isn't it kind of like the halting problem? Like you never know what you'll encounter until you get into the program.
Yeah. Yeah, it's difficult to know what we'd run into until we actually optimize it and then see what happens. Yeah. So I really like this thing they have on I think it's the third page of my printout here. That they have this thing that says warning. After 3 levels of inlining, potentially across files with link time optimization, some common expression elimination, after hoisting this thing out of a loop and proving that these 13 pointers don't alias, we found a case where you're doing something undefined. This could either be because there's a bug in your code or because you have macros and inlining and the invalid code is dynamically unreachable, but we can't prove that it's dead, right? So at the end of the day, it's really difficult to give a useful error when this happens, because of the fact that, like, you know, this one is not too bad, we ran redundant null elimination first, which eliminated this code. And then we ran dead code elimination, which eliminated that code, which left you with no null check before your pointer access, right? Even that is kind of complicated and would be difficult to read as a programmer. Like if you compile your code and then you get a report afterwards that says like, this is what we did. How many of you would read that consistently? Now there may be, if you have a job and it's your job to read it, you might read it more. But at the end of the day, this would be very difficult to sort of parse. You'd have to have at least, some knowledge of compilation and what all of these things do. And even then it might be difficult to understand, like, wait, why did my code end up in this particular state after these optimizations happened? So it's sort of difficult. I think the crux of the problem is it's really hard to tell a programmer what happened as undefined behavior here. Now this is becoming sort of a bigger thing that like more compilers are trying to handle in a reasonable way. So there's a compiler for ARM, the ARM HPC compiler, like high performance computing compiler, now has a thing called basically reports on the optimizations that were performed that tries to sort of indicate to you what it did in terms of using undefined behavior, in terms of optimizing the code, so that you can then sort of parse through those and try to figure out what happened while it compiled your code. So that's sort of, the step in this direction, basically, to be able to tell the programmer in a meaningful way, like, what happened as we optimized your code and why did it end up doing what it did. But it's still a very tricky problem to try to solve. So that's all I wanted to talk about with this. Again, hopefully, I think this was, hopefully this is a useful article to have read. I think it's a really interesting take on sort of C and C++, which you're familiar with, and then optimization overall. Any other questions or thoughts on this blog post? Okay. So just for logistic stuff, I just wanted to remind you that the labs are going to be due on Friday of this week. So please make sure you are working on those in advance. We will have a full lab day tomorrow sort of to catch up on labs 5 and 6. Lab 4 is canceled unless you did it already, in which case the two of you that finished it, or if you would like to finish it still, you can get extra credit towards your other labs and or assignments. So that'll be, both of those will be graded on as part of 12 weeks, which should be in by Monday of next week. So please make sure that you have those done in time so that I can include them in your grades. Otherwise, if there are no other questions, I will, I'll be on Discord tomorrow like normal. That we can't be in voice while you're connected to the remote server, but I'll be there to answer questions. And, if you have questions and want to jump in voice and disconnect for a minute, you're welcome to do so. So I'll be around. And then Wednesday, we will dive into the back end of the compiler and talk about instruction selection and scheduling. So I will see you tomorrow. Have a good day.
Can we just drop those labs into the submit folder on the server?
Yeah, that's fine. Just make sure they're uniquely named.
Okay, perfect.
Yep.
So intro to optimization is lab 6, right?
Yes.
And the LVM IR lab was lab 5.
Yeah.
Okay.
Yeah, which I have from you. So I think lab 6 is the only one you're missing right now.
Okay.
And you were pretty close to done with lab 4, I think, right?
I don't know exactly where I was.
Okay.
But I don't have like the assignment. I don't know what the assignment is.
Okay. Yeah, so I mean, if you want to turn in what you had from lab 4, I can give you some credit for it, basically. So if you want to turn in where you were, it won't hurt you, basically.
Like some extra credit?
Yeah.
Okay. All right, I'll do that.
Okay.
Do you have like the assignment for Lab 4 as a
I
good
do have the
PDF
assignment for it. Yeah, I can pull that up real quick here.
But
And link it.
Professor, can we use your EI schedule thing still? Like, is
Yeah.
that still up to date? If we want to work on, if we have questions about the lab or anything?
Yep. It should
Alright.
still be fully up to date. So yeah, feel free to schedule if you want to.
All right. Thank you.
Yeah, no problem. Okay, yeah, I have the link here. I'll put it in.
Okay. I'll I have to like refresh myself on where I was because I haven't worked on it in a while. But if I'm like close and I see where to go, I might finish it.
Okay.
But if not, I gotta see how much other stuff I have this week. But if I have time, I'll finish it. If not, I'll just submit what I have for Lab 4.
Yeah, no pressure. I think I checked to see like where everyone was at, and I think yours was pretty close to done, if not done.
Okay.
So I think you were, close to getting the extra credit, which means you might as well if you can. So cool.
Okay. All right. Thanks.
Yep. See you.
Yeah.